Now that we've seen how to build very simple models, let's look at how to use simple models locally. And Lime is a very nice example of that. And here's how it goes, right? So it assumes that it, takes as input a black box classifier, and that black box classifier can be very complex. So for instance, such as a, boosted, stacked, bagged version of a combination of classifiers or regressors or sequence annotators. So it can be some, fairly complicated thing. And in general, it's mission impossible to approximate it well. But the idea is that even if you have some very complicated function, you can quite conceivably approximate it linearly, locally. And so we have our model, it gives us some predictor, and then we would like to get an explanation. So for instance, if the model says you have flu, then maybe the fact that, you're sneezing and have a headache and you do have fatigue or are not fatigued. And then in the end, of course, the human is supposed to make a decision, but we're mostly concerned with the first three steps here. So for instance, for, a decision surface that is, nonlinear in some interesting ways, you could always locally try to approximate it. So obviously, if you were here at this data point, right, then maybe this would be a good linear approximation, or maybe here it would be something like this. And you can clearly see that there are areas where this doesn't work so well. For instance, what do you do around here? Is it this line, or is it that line, or is it that line? So those models have a limited applicability. Nonetheless, it's much better and also easier to understand, at least locally, what's going on by means of some linear, possibly sparse linear model. So basically what you can do is you can take all those tricks that we discussed before, where we looked at, simple models, and you apply them locally. And the idea then being that if you apply them locally, let's say if this is this cross where we care about the data, you take some neighborhood, and then within that neighborhood, you try to approximate the data by a linear model. And this actually works rather beautifully, or at least it does so on the examples that Ribeiro et al. Had in their KDD paper from 2016. So they got actually a best paper prize for that. So basically they start out with some original image, and yeah, this is basically a Labrador playing the guitar, and it's an acoustic guitar. Well, and this is essentially early deep learning. The idea would be then, can we explain, why we think this is a Labrador or it's playing a guitar? And it turns out that, basically you use this tagging model, and then for every tag or successive tag that's being generated, you try to find a linear classifier that would lead to this one. And quite serendipitously, you get a situation where, electric guitar or acoustic guitar and then Labrador are suitably explained. I mean, it's very clear that this model isn't perfect because, for instance, I think we can all agree that this doesn't particularly much pertain to something being a Labrador, or likewise that, for the acoustic guitar, that component is maybe not so meaningful, but, it's better than nothing, and humans quite like it. So this is a simple linear model, and one thing that matters in this context is whether, let me just go back one more time, by how much the value of x really varies. So for instance, if I have, some number like x equals, 100, then x equals 100 can be a large number. But if I told you that x naught is 99, well, that would mean that maybe x isn't such a large number relative to its average, because the difference is really just 1. Whereas if I told you that x naught is 0.99, then you would probably agree with me that x is a comparatively rather large number. Okay, how does this matter? Well, in the same way as you would say, well, let's annotate that image, you might very well say, well, let's build a linear model, but also with a good reference baseline of what the good value is. But the question is a little bit, what should you pick? Should you pick the mean, or should you, and because the mean may not be particularly meaningful, it may not even, correspond to valid data, or, should you sample some reference data conditioned on the variables that you want to explain or not explain? So there are lots of tricks. And before we dive into more details about, which explanation exactly to pick, I want to give you a brief primer on dependent random variables and how they actually come into play here with, feature explanation. So let's start with, the issue of having a good reference term. So let's say we have, this influence of variables, W transpose X plus B is, sum over I, Wi Xi plus B. Then the influence should really be based on the change in the value, so delta X, as opposed to X proper. And as such, we need to determine what the reference value X naught is, such that we can compute delta X, because delta X is, X minus X naught. Now, if we have data that's, reasonably, independent-ish and tabular and all of that, then, that may be a good idea. It may be a little bit more tricky when we have an image, because I cannot just go and, rip out a patch from the image and say, well, fill in any arbitrary other patch, because in many cases that patch will not work. It'll basically look like a whiteboard or a carpet that you've repaired by patching in something else. So in short, the data type matters, but in general, what you really care about is to have, that reference X naught, such that we can then find out whether, X amounts to a small change or a large change. Because it's clear, even though, in total X is smaller here than there, the change is larger. Okay. So that gets us to the question, how should we go and measure, the influence of Xi? Because if I change Xi, well, you could assume that all the other variables also change, right? So what we really care, one can argue, and I think that's a good point, is we care about the direct influence of Xi on the output, as opposed to whether changing Xi really affects something else, which then affects things. So I basically now have two choices. I could either ask for the conditional expectation, right? So that deals with the, I have an image, right, of Stickman. And if I go and, cut out parts of Stickman's arm, then it's clear that you cannot just go and replace this by another photo, which is just, a photo of a little cat. Yeah, okay, I'm sorry, I'm no Picasso, but I guess you get the idea. So, I mean, yeah, okay, that looks funny. Maybe it's a cat eating that dog's that person's arm, but since those things don't quite happen that frequently, it's clear that filling in something arbitrary is maybe a dumb idea. So in that case, asking to use the conditional expectation might be the right question. But then the alternative is you might want to use the marginal. In other words, just independently fill in some reference terms. And what I'm going to show you is that maybe somewhat counterintuitively, the latter, namely the marginal, is usually the right idea. Okay, let's motivate this a little bit. Suppose I have some latent variable and I have two observed variables, x1 and x2. And conditioned on that latent variable z, x1 and x2 are conditionally independent. And so, but if I look at, the distribution of the observed, so x1 and x2, well, they are clearly dependent on each other. So in other words, p of x1 and x2 is not p of x1 times p of x2. Okay, so this sounds, fairly abstract. Let's look at an example. So here we have three gentlemen, and they look like, they could be politicians or whatever. They all look, serious. And you could ask the question, are they trustworthy? Because maybe if they're trustworthy, you'll buy an insurance from them. So x1 would be the photo. apologize, this kind of gives away the story. So if this is x1 and x2 is whether they are trustworthy, there might be, an underlying latent attribute which, governs, whether they've done something bad or had a good life or whatever. But, usually if we see somebody, who wears a suit and so on, most people are inclined to assume that that person is trustworthy. This is why politicians wear suits. Or if they want to convince somebody, who is poor, then you get billionaires wearing a trucker hat to pretend that they're one of them. Right? Or they will even grow like a, stubble beard and get on a truck. So now if I showed you those photos, you would probably recognize who those three not so upstanding citizens are. They're three murderers who killed Ahmaud Arbery, right? So they're vile criminals, and so they're clearly not trustworthy. But since we don't observe, their guilt or not, what happened is that in court, their lawyers dressed them up like, people who look more trustworthy in the hopes that they would not be found guilty. And, it's clear that they did a fine job on the optics, but fortunately the legal system worked and used evidence rather than appearances and found them guilty, so they will rot where they belong. Okay. Maybe let's look at another example. Let's say we approve a credit rating, and if I have a customer coming in what's charmingly called a wife beater, so that's the outfit on the right, or coming in an Oxford shirt, well, probably the person in an Oxford shirt might do better in the credit application, right? But at least it's, it's an attribute of that person, and, usually credit rating may, or, creditworthiness may manifest itself also in, the outfit. But obviously it's clear if I take the gentleman on the right and, let him wear a shirt, he does become no better or worse in terms of his creditworthiness. So I really should go and, not take that into account. So if I basically fix this by giving that person, a different outfit, well, I don't really change anything on the underlying causes. So therefore, it shouldn't really have any effect. And so you should really go and draw, the other variable independently rather than conditioning it. That's not always the case. So for instance, if you work out, well, you get fit and then you can run faster. So in this case, if x1 is working out, x2 being able to run quickly, and, f of x being, or y being, whether you're fit, then, it's clear that there is a dependence. So be careful when you perform some of this analysis that you know what you're actually doing, because otherwise you might actually, come up with bad estimates. So there's this very nice paper from Yansing et al., which looks exactly at that, and it phrases this in the context of Proust's do operator. So the do operator, which is basically, set a variable to something while keeping the rest the same, what it does is it basically severs this connection here. So the do operator basically just goes and integrates over dp of x2, x3, so the marginal, and it takes then the expectation of y conditional x1, 2, and 3 as if things were okay, but basically the do operator for x1 sets it to some value and then cuts the edge. In graphical model terms, therefore, if we have a situation that looks like this, just go and sever the edges from the variables whose influence you want to know, and for the ones that you want to leave out, just draw them independently. Turns out this is actually much easier to do, and it's also more correct. And well, this helps avoid spending a lot of computation and writing code and models, to approximately, you sample from the conditional probability, and people did that in something called SHAP, and we'll get to that later in this class. And basically, Janssen et al. Just proved that the simple hack that the authors of SHAP implemented is actually the correct one. But the idea applies much more generally rather than just for SHAP, and as such, you should just go and draw independently as a first rule of thumb.